Well, good morning and good afternoon to everybody. This is the acquisition panel number 16 for our acquisition research symposium here at the Naval Postgraduate School. I'm John Hammerer. I'm the chair of Integrated Air and Missile Defense. If you are in this class mistakenly, it's okay. You can stay here. I think you're going to find it to be very enjoyable. I know that I'm very excited about this one, and the reason is I spent 8 years in the Office of the Chief of Naval Operations, Surface Warfare Division, where it's all about operational requirements and how to fund them. And additionally, I teach a combat systems engineering course here where we consider very carefully the importance of operational requirements and how they are flowed down to the design of combat systems. So without further ado, I'd like to introduce our two speakers here today, Aditya Singh and Jonathon Miller. So over to you, gentlemen, to introduce yourselves. Aditya.
Yeah, thank you, John. So my name is Aditya Singh. I'm a PhD student at the George Washington University in Washington, DC in the Systems Engineering and Engineering Management Department. And I'm also a National Science Foundation research traineeship fellow as well. So.
Great, welcome. Jonathon, over to you, sir.
Jonathon Miller, I former submariner. After being a submariner, I went to college. Have an undergraduate degree in structural engineering from UCSD, master's from RIT. I'm a PhD candidate at WPI. I currently work for Naval Information Warfare Center Pacific as a system engineer. Over.
Very good. So with that, Aditya, can you start for us and tell us about your work?
Absolutely. So let me just get my slides up. Can everyone see my slides okay?
Yes.
All right. So the goal of my research broadly has been to understand how complex physical systems are changed, and particularly in the post-production phase, and I'll talk about what that means. So this preliminary work I did with my advisor, Zoe Shane-Farber, who's the professor and chair of the department. And so I'll just get started. The broad research motivation for us was that we know that a lot of these complex engineered systems have long life cycles, protracted development times, and high unit costs. So in essence, they're very expensive, hard to make systems that often last a lot longer than we expect them to. And because of this, they're often tasked with things that were not originally designed for. So one of the classic examples of a system like this is a C-130 aircraft, which was originally designed as a medium cargo transport during the Korean War, but has since then been modified to be a gunship, to fly into the Arctic, to do reconnaissance, to do satellite recovery, to fly drones. So in essence, we know that systems, especially these complex engineered systems, are often tasked with capabilities that they weren't originally designed to have. And so when we look at acquisitions today, a lot of our acquisitions focus on, how do we buy a new system? How do we buy new capability? And so, you'll see something like urgent capability acquisition where, okay, we need to field something in less than 2 years and get it, out to the field to support the warfighter. But there's often this sort of change and acquisition that happens in the operations and sustainment phase as well. And this is what we're calling post-production change. So there's often a need to provide new capabilities to existing systems that are in the field very quickly. So a lot of the times with these aircraft or with any of these systems, the unit cost is too high and the development times are too long to immediately field a new system to meet a new capability need. And you need to get capabilities perhaps without the ability to recall a lot of these systems to service depots to make these changes. So this is what we're calling post-production change. And so when we look at the academic literature on changeability, there's a lot of different strategies for changeability. I'm not going to go into all of them. I'll just talk about the two that we discuss in the paper primarily. And those two are modularity and changes to your ConOps. So modularity is sort of the loose coupling of components that do different tasks. So you can imagine if you have a phone is a classic example of modularity. If you wanted to create, for example, component swapping modularity, you might have your phone as a platform, but you might switch out the color of the casing around the phone to make a new phone, quote unquote, a new system every time. So that's a very highly modular design, right? If the case is one color and you swap out the case, you can have different color phones without designing new systems. Similar thing with component sharing modularity. So the same charger port might be used across different systems. These can help you, maintain economies of scale and things like that. And also if something can be easily swapped in and swapped out of a system, you can also gain new capabilities that way. That's a classic example of changing the form of your system to gain a new capability. Another way you can change is through changing the function of your system. So I always like to use the silly example of a screwdriver, even though it's kind of silly. So if you think about it, you can use a screwdriver to screw in a screw. And if you're like me and don't have a lot of tools at your house, you maybe had to use a screwdriver to hammer in a nail or to open a can of paint or something like that. So you're gaining a new capability with your screwdriver without actually changing the form, because you're changing how you use it, the operations, the functions of the system without changing the form. So we see that across the literature, we see form and function both being able to change systems. And so we wanted to empirically test these changeability strategies to see how do they actually work, and especially in post-production change where you have to innovate very quickly without the ability to bring things back into service and to modify them extensively for months on end. How do these strategies really work in that context? And we decided to look at close air support during Desert Storm because it provided us with a natural experiment to study this, because many aircraft were modified to do the same mission during the same time period in the same operating environment. And we decided to pull out 3 essential categories of change based on doctrine that we analyzed. That was effective weaponeering, effective targeting and marking, and flexible control and prompt response. And essentially, we sort of looked at 4 aircraft, or we identified 4 aircraft that performed this mission in Desert Storm. These 4 are the F-16, the FA-18, the AV-8, and the A-10. So the F-16 is a multi-role fighter. The FA-18 is a fighter and attack vehicle, which is why you see the F/A designation. The AV-8 was primarily designed for close air support, but also for vertical takeoff and launch. And then the A-10 is a classic role specialist, as it was designed primarily for close air support. So you can see just by looking at the different aircraft that perform close air support during Desert Storm that there's a variety of multi-role and role specialist aircraft. So this also lends to our natural experiment, because the aircraft that ended up performing close air support in Desert Storm were all designed to different levels of optimization for the mission. And so we decided to analyze by reading a lot of the DoD Gulf War Air Power Study, which was the sort of official report after the Gulf War, to determine how effective or ineffective our air power was, to see how these 4 aircraft perform in these 3 categories. And so where you see X's are places where we identified the need for a post-production change that occurred during the war, and the places where you see a D is where a change was not needed or the need did not arise. So we say that the design of the system originally seems to have met the goals of the mission adequately. So that's what you'll see here. I'm not going to talk about all the changes, but I'll briefly go over 3 to sort of illustrate our findings in the paper. So the first example I'll talk about is effective weaponeering with the F-16. So there was a need and a want from the Air Force to have the F-16 have more gun power than it did to do close air support. So they tried to take the gun from the A-10 and modularize it into this gun pod that you can see in this diagram, and then you can see it attached to the center line of the airplane as well. So basically they took the A-10's large cannon, shrunk it down, modularized it to a pod that could be attached to the bottom of any tactical fighter, and this was called the GPU-5A pod. So this pod was rolled out for the first time in Desert Storm and was actually a failure because the pod itself was not really well integrated into the F-16. So when the pod was firing on targets, the vibration from the heavy cannon was so heavy that the pod would shift and slump offline, and that would mess with the targeting controls on the aircraft as well. And overall, it was just too big of a cannon to be on the F-16. It was not properly integrated, and it was abandoned after 1 day of use. So we can see that the F-16 modularity example here really didn't work because the module itself was not properly integrated into the F-16. But one example where modularity did work for the F-16 was the Lantern pod. So again, similar concept. You contain a system within a pod and quickly attach it to your aircraft and try to gain a new capability this way. The capability they want to gain here was nighttime operations. So sure, a lot of us remember that one of the biggest takeaways from Desert Storm was that the US could very effectively operate at night. And we were able to deny the Iraqi forces the cover of darkness, which was something that they talked about a lot after the war as being one of the reasons why that operation was so successful. So the Lantern pod essentially contained a forward-looking infrared radar that hooked up to the bottom of the aircraft and provided an infrared image in the cockpit, as you can see in that picture. And so this actually really enabled the F-16 to fly at night with minimal changes to operations. And it was actually very successful on the F-15 as well. So this is an example where modularity actually works really well because they attached this module. It was integrated very well into the cockpit of the F-16 and allowed for nighttime operations rather easily. And so an example of changing your ConOps to achieve a new capabilities with the A-10. So the A-10 also needed to do nighttime operations during Desert Storm. So originally the A-10 pilots who were tasked with figuring out how to do nighttime operations decided to fly in tandem and drop flares. So one person would drop flares and the other person would shoot at the targets that were illuminated by the flares on the ground. This was a tactic dating back almost to World War II. So pretty rudimentary, but one of the pilots realized that the A-10 received this missile called the infrared Maverick missile. And this missile had a infrared TV seeker on the head of the missile that would kind of act like a forward-looking infrared radar, but in weapons school, they had instructed the pilots never to look at that infrared radar as a forward-looking radar because the field of vision was so narrow. So the instruction officially was to acquire targets from your window and only then make sure that you're properly locked on using this infrared TV. But what the A-10 pilots quickly realized is that obviously at night, they can't visually acquire targets as easily or if at all. So they decided if they flew high enough, they could avoid being detected through sound or visually. And they could then use this infrared radar, even if it had a very limited field of vision. Because if they flew high enough, they weren't really worried about getting hit from the ground as well. So basically, they sort of turned US Air Force instruction on its head to achieve nighttime operations. So they would fly again in tandem with one pilot using their Maverick infrared radar to seek out targets and then fire while the others were sort of keeping watch to make sure that nothing went wrong. So again, like I said, it does have a very narrow field of vision. And so this is a better example of you don't always have to make very, risky changes to form to achieve new functions. And so looking at these changes and the other changes that we look at in the paper, we can see that modularity isn't the silver bullet for changeability that it's been described as in the literature. There's a lot of practical considerations that need to take place to understand how modularity really works and how it can really be effective in your system. And the type of module you might want to add on in the future needs to influence the design that you plan for when you're in the design phase, right? So there's a question as to should the F-16 have even had that big of a cannon tried to be installed on it in the first place. If you look at the design of the A-10 was specifically designed around its large cannon. So the idea that you could take that cannon, miniaturize it, and modularize it for a multi-role fighter that was, designed for air-to-air combat as well, might seem ludicrous because you just know that airframe can't handle that big of a cannon. Another thing that we realize is that ConOps changes are a really important pathway of post-production change. And this is also something that's not really discussed very well in the literature. Most literature focuses on changes to form to enable new capability gain. And like you've seen with the two modularity examples we talked about, changes to form are often very risky, and there's a lot of research done, both in academic literature and from the DoD on, changing your form well after the design phase just increases cost exponentially and is incredibly risky. So it should only be done in the most, absolutely necessary situations. And we also realize that there's some interaction effect between how well you can change your operations and the form of the system. So for example, looking at the A-10's nighttime vision or nighttime operations, if they don't have that Maverick missile, then they can't do that ConOps innovation, right? So if they don't have that form of the system, they probably have to resort to dropping flares and firing that way. So we know that ConOps changes don't exist in a vacuum. They also do depend on the actual form of the system. So this is still very preliminary work. And we're hoping to deepen our current case studies because I'm sure we didn't capture every single post-production change that took place during Desert Storm. And we're also looking at the C-130 as well. So the dichotomy there is that the C-130 is a single aircraft modified to do many missions, and this is many aircraft modified to do a single mission. We want to look at these empirical studies together and see what we can draw out from, how do these change enablers really work and what really enables post-production change. And we also want to look at other settings going forward. So with that, I just want to thank you for your time. And if you have any questions or comments outside of this panel, of course, then I would love to get in touch and welcome any collaboration. Thank you.
Well, thank you very much, Aditya. That was most informative. I'll tell you my immediate takeaway from this, three big things. The first is how important it is to really understand our history. Often, especially in the engineering world, we tend to focus on the technical and maybe not so much the history, but the history is very, very informative. And as they say, those who don't know their history are condemned to repeat it. The other thing I thought was very interesting was the importance of the how and the why. So how and why the A-10 was designed and built, how and why they tried to put these capabilities onto the newer aircraft, but then even at a deeper level, I think many in the audience are familiar with things like the military standards and military standard or MIL standard 901, which is all about shock and vibration. So when you think about, those kind of fundamental things, knowing the how and the why is just so important, and not to criticize. I mean, never criticize these guys who are in the path of danger, trying to do things in chaotic and confusing situations. But wow, if somebody had really kind of thought about 901C and applied that, and they probably did, but it was all about the risk, right? We've got to get the capabilities and we've got to get it fast. So something to taking the risk. The third thing I took away was the importance of innovation, right? So we come to war, you fight the war with the Navy that you have or the Air Force that you have, not the one you want to have. And so this is where critical thinking and innovation are just so absolutely important. And I think that's one of the things that the officers at Naval Postgraduate School are challenged with every day, to do the critical thinking and to do the innovative thinking. So anyway, great brief there. And what I would say is that I see the questions are starting to fill up in the question and answer file. We will get to the questions and answers as soon as we're finished with the next presentation. So with that, over to Jonathon Miller. It's your turn, sir.
So hi, everyone. My name is Jonathon Miller. I want to thank the Acquisition Research Program for allowing me to present my paper, which is titled Correlating a User Experience System to Product Success. This is also the title of my PhD dissertation. So I covered my background beforehand, so I'll skip over this. So in developing the research question, I looked to similar products and wondered why some products were more successful and others were not. So for example, with all of Microsoft's resources and talent, the Zune, a music player developed by Microsoft, was not nearly as successful as anticipated. However, the iPod, a music player developed by Apple, was very successful. So why did the iPod succeed while the Zune failed? Well, after reviewing various products from a systems thinking perspective, a pattern started to emerge in which it seems that successful products more holistically address non-functional requirements that emphasize a user experience system. So therefore, a natural test and control group can be identified. The test group are those products which seem to implement a user experience system, while the control group are those products which seemingly do not. In addition, the independent variable will be evaluated by the degree to which a user experience system is considered in an end product. So a Likert style scale with surveys will be used to perform this evaluation, and this will be discussed in more detail in the following slides. And regarding the dependent variable, success, an appropriate measure will be taken, such as revenue, via setting a global scale. A score between 0 and 10 will be obtained. A Spearmint correlation has been identified as the means through which I'll validate my hypothesis, which is product development teams are more successful when they identify their products as part of a user experience system, which holistically address non-functional requirements. Also, for the purpose here, a user experience system is a system that has been strategically developed to optimize the experiences that are important to the user by identifying the user as the focal point of the system in terms of the goals the user is trying to achieve and the environment in which the user is operating. The Spearmint correlation is subsequently described in more detail, but it should be noted here that the Spearmint correlation establishes how well two variables are ranked in comparison to one another for a set of given observations. So for example, if two pairwise comparisons are made, then there are 4 observations which are comprised of 2 dependent variables and 2 independent variables. Additionally, if the products that are ranked first through fourth for the degree to which a user experience system, in other words, the independent variable was implemented, are also ranked first through fourth for the product success, in other words, the dependent variable, then there would be a perfect Spearmint correlation and provide a score of 1. So here R is a Spearmint correlation, and the closer R equals 1, the more positive the correlation, which would confirm my hypothesis. The closer R equals -1, the more negative the correlation. And if R equals 0, there is no correlation. The sample size needed to utilize the Spearmint correlation has been identified based on a process proposed by Douglas Bonnet and Thomas Wright. It has been found that 40 products are needed, which means 20 pairwise comparisons are needed. And detail on the process for obtaining this figure is beyond the scope of the presentation, but I can provide that upon request. Participants will be used with the goal of removing bias from the Spearmint correlation analysis. Therefore, to remove bias, the Likert-style scales will be used in which participants provide a numerical score indicating the degree to which the independent variable, in other words, the user experience system, is present in a given scenario. And additionally, while training will be provided to the participants, their training will be based on my interpretation of a user experience system from both researching the samples and writing the surveys. And as previously stated, I've gleaned the concept of user experience systems from a selective review of successful and unsuccessful efforts, while ensuring that the concept of user experience systems is both rooted in system engineering and applicable to systems thinking, which means the efforts to establish the user experience system have necessarily been qualitative. So this implies that while Likert type scales are quantitative tools, the underlying research is qualitative. So future efforts, qualitative research will be supported by quantitative tools meant to mitigate bias with the use of participants. It has been determined that the number of participants should be the same as the number of comparisons, and that's 40. And to arrive at 40, a statistical analysis has also been conducted, but that's beyond the scope of the presentation, and I can provide that methodology as if requested. So again, after reviewing various products from a systems thinking perspective, a pattern emerged in which it seems that successful products more holistically address non-functional requirements that emphasize a user experience system. However, when considering requirements, it is much more intuitive to focus on functional requirements, which are those requirements that technically state how a product is supposed to perform or what a system is supposed to do. The non-functional requirements, which are quality characteristics that are desired in a product that define how a product is supposed to be. And while there are some non-functional requirements which engineers typically realize are important or attempt to incorporate into designs, for example, there's RAM, which is reliability, availability, and maintainability, there is not an overarching approach that facilitates selection of non-functional requirements needed for product development. In addition, the literature indicates that there is no agreement on a comprehensive and complete list of non-functional requirements. So after conducting a literature review in which attributes have been gleaned from successful product development efforts, which seemingly provide a desirable user experience system, the figure on the slide was developed, which illustrates the user experience categorization for non-functional requirements. Additionally, the figure on the slide was also developed with the previously defined user experience system in mind. And when this was done, alignment to a user experience lifecycle emerged, which extends from acquisition to use and support. Also shown here is an example of the non-functional requirements that have been identified for the achieving goals user experience categorization. Each product under consideration will be assigned values from 0 to 4 pertaining to the degree to which these non-functional requirements are present. Additionally, precise definitions for each non-functional requirement has been identified. So shown here is a subjective example from the paper. In the paper, the degree to which the iPod or Zune has non-functional requirements from each user experience categorization embedded within their design is ranked from 0 to 4. This again is the independent variable. Also, with respect to success, which is the dependent variable, this was objectively determined via revenue for both the iPod and Zune and converted to a global score via linear interpolation. For brevity, the analysis for the iPhone and BlackBerry are not demonstrated in the paper. However, the results are shown to demonstrate the Spearmint correlation. Within the Spearmint correlation equation, N is the number of each observation. In other words, twice the number of pairwise comparisons for both the test and control product. And D is equal to the distance between the success rank and the user experience rank. Every observation will have a user experience score and a success global score, which will be ranked after all of the observations are made. Once the ranking is complete, the distance between the user experience score and the success global score will be identified and placed in a column titled D of the Spearmint correlation table. D will subsequently be squared for the purposes of the Spearmint correlation equation and placed in a column titled D squared. After every observation has a D square value, D square will be summed for the entire data set. For this example, when all the values from the table are placed in the Spearmint correlation equation, the Spearmint correlation is 0.8, which implies a positive correlation and confirms my hypothesis. If it is found that products are more successful when they are designed to be part of an overarching user experience system, engineers will be better equipped in the early stages of design, especially when translating stakeholder requirements to system requirements. By generating a more robust set of requirements through a user experience system perspective, there should be less churn due to updating missed requirements as the design progresses. However, while better transitioning from stakeholder to system requirements is significant, the more impactful contribution is demonstrating that success is linked to the degree to which a product is part of a user experience system. If it is found that success is linked to the degree to which a product is part of a user experience system, then it will behoove informed product development teams to holistically consider and embed non-functional requirements into their designs. So the current level of hostility around the globe has not been experienced in over 70 years. Additionally, while threats are seemingly increasing, funding to the DoD is decreasing primarily due to increased fuel cost and inflation. So for example, as quoted by Taylor and Gross from the Federal Budget IQ, quote, President Biden's $715 billion fiscal year 22 budget for the Department of Defense assumed 2.2% inflation and a 10.1% increase in fuel cost. With inflation closer to 7%, and with fuel costs for the world's largest purchaser of fuel up 30%, DoD faces a $40 billion second half hole in its fiscal year 22 budget. For perspective, the fiscal year 13 Budget Control Act's DoD sequester totaled $37.2 billion, unquote. Therefore, in my opinion, now is the time within the DoD to specifically think in terms of the warfighter's experiences and building systems which efficiently maximize those experiences. With respect to the DoD and the user experience categorization, I've listed here some overarching relevance between those two categories. For acquisition, cost and schedule are critical, but performance should be viewed in the perspective of the end user. Regarding initial use, the efficiency with which a system can be learned is prioritized via a user experience perspective. And concerning utilization, the system must reliably operate in a usable and safe environment, and within a system of systems environment, a system must be able to interoperate with other systems in order for the warfighter to achieve the mission's goals. And lastly, the system design should account for maintainability and serviceability, which should extend the longevity of the system and provide adequate return on investment. With respect to my next steps, I need to identify the statistically relevant set of pairwise comparisons, create a survey for each observation to determine the degree to which a user experience system has been implemented, obtain objective success data for each observation, and test out my surveys by providing them to students taking a graduate level systems thinking class, and evaluate the initial survey's effectiveness. In the intermediate, I will complete the dissertation pertaining to this topic. And in the long term, I hope that the lessons I learned from my dissertation can help assist efforts within the DoD. That concludes my presentation.
Well, thank you, Jonathan. That was most informative. And again, a couple quick takeaways, at least that I had, and that was, I believe, the very, very important aspect of early user participation. And so in our world, in the naval world, this means that we really want to have the operators, the tacticians, the warfighters working closely with the engineers as they come up with these new capabilities. So to your point, right, the user experience and the importance of having the users involved. Another thing which I think is very important, and you've done great work here, is the importance of the quantitative measures of these user experience. So I can tell you from experience, increasingly, the Office of the Secretary of Defense and that staff, as well as the Navy, is relying heavily on quantitative analysis. I think it's a case of while we were somewhat comfortable with the gut feel, as we say, in decision making, the fact of the matter is that technology in progress is so rapidly evolving at this point that gut feels based on experience may no longer be enough. If you think about it, with slower pace of change, decision makers had a very, very large amount of experience. This was perhaps anecdotal, but over the many years, when things aren't changing very much, they are able to accumulate a great deal of experience when it comes to decision making. Today, things are moving so rapidly, and the margins are so thin when it comes to making these decisions that data-driven decision making is really important. So your work in this area is, I think, most helpful and very, very relevant. So with that, it's time for the question and answer period. And so what I'd like to do is open the floor. I'd like to call on those who have asked the questions to maybe turn on your camera and ask the question if you are so inclined. First, I'd like to go to Gabriella Blott. She has a question for Aditya. Gabriella, could you turn on your camera perhaps and ask the question?
Let me enable her, sir.
And for those who are unable to ask, I'd be happy to do that for you. I've already gotten one from Mr. Bublinski. So Gabriella, looks like you're there. Over to you. And if you're bandwidth limited for the camera, don't worry about it. Okay, maybe I can ask it for you. This is from, again, Gabriella Blott, who says, for Aditya, how do you think stealth influences the ability to design for changeability?
Yeah, I mean, that's a good question. You know, when we think about stealth, I always like to frame it as it's either revolutionary in that it's a new capability that we've never had, or it's revolutionary in that it's a design constraint that we've never had. I could think about it as the latter rather than the former, because I think being less detectable isn't a new capability. I think it's just a better iteration on capabilities we've had before. But it is a revolutionary design constraint that we've never had before, right? So if you look at the design of the F-22 and the F-35, every single module that you attach onto it has to be contributing to the stealth of the aircraft, right? So you can't have a stealthy aircraft and just have a ginormous module on the bottom, well, because that'll just give you away right there. So I think it influences the ability to design for changeability in that it adds heavy constraints onto the design of the system. But a lot of these stealth platforms are also becoming more software reliant and software based. So a lot of our older legacy systems are primarily hardware based and have a software component. Now software is becoming just as important part, if not more important than the hardware. And you can actually do a lot of cyber physical change. So, you know, if I make my software better, I might see an improvement in the physical performance characteristics of my system. And that's something that we're looking at actually with the National Science Foundation currently, but that's an area that remains to be seen. But I think that cyber changes will augment the limitations of changing physically now.
Okay, thank you, Aditya. Hey, I think what we'll do, just for purposes of consistency here, I'll read out the questions and allow our presenters to respond. This one's for Jonathon, and it comes from Adam Pollock. And Adam would like to know, did you do any analysis on non-commercial applications? Do you think that an analysis is possible on a system where success is more difficult to objectively define or is dynamic, unlike revenue created?
Thank you for the question. So no, I haven't done any analysis on non-commercial applications yet. And to your point, the system success where it's more difficult to objectively define. So unlike like revenue, right? So I think what you're alluding to there too is possibly like, how are you going to have a test and control case potentially for military systems, right? And so that was particularly the reason why I'm analyzing this from a commercial perspective, because of the ability to get like you say here, revenue data, right? So you know, with revenue data, it's objective, it's hard numbers. In the paper that I have, the revenue data, it can for the BlackBerry and iPod is staggering, and that revenue data is pulled from SEC requirement, reports to SEC, Security and Exchange Commissions. Those are those reports, and so all that is hard data, and what I hope though is that if I'm able to show, at least in the commercial sense, that that the user experience system is without a doubt correlated to success, then that could be a case that could be made to get the attention of decision makers within the DoD, and then that would facilitate any lessons learned from this work to translate to the DoD, and again, that would be the hopeful transition that I would like to see. Over.
Okay, thank you. This next question is for Aditya. It comes from Mike Good, and Mike would like to know, and it's open for both presenters. So the Navy is prioritizing flexibility and adaptability in its design for future surface combatants. One of the challenges has been that's been encountered is how to state these attributes as requirements. What SMART, and SMART is an acronym. SMART stands for specific, measurable, achievable, relevant, and time-bound. What SMART metrics would you suggest could be implemented for flexibility and adaptability?
Yeah, so that's actually a good point and has been one of my major frustrations with this literature in general. So in the design for changeability literature, you'll hear people talk about primarily robustness, flexibility, adaptability, and agility. As for, areas of changeability that we really want to have, but no one really talks about what does that truly mean for a system. And a lot of times, if you will see papers with different metrics in them, there's sort of very vague metrics that are sort of hard to interpret. Is something more or less changeable because it's more or less modular? Maybe, maybe not. How quickly you can actually put modules on and take modules off is a question. Is your flexibility going to be the flexibility of your system, or is it going to be the flexibility of the fleet, right? So I could say that I'm going to have, 40 very flexible aircraft in my fleet, or I could say I'm going to have 10 different types of aircraft in my fleet, and that's where I get my flexibility from. So a lot of these terms that we sort of all aspire to do are also very vague, I'm finding, and that the metrics for them are very unclear and highly theoretical. And one of the challenges that we identified is that a lot of these systems, you don't always know what the threat is going to be when you actually field them. So, if it takes you 20 years to design a system, we've seen that the geopolitical landscape can change very much in 20 years. And there's also that old adage of you're always doomed to fight the last war that you fought, and it's hard to see the next one coming. So I probably don't have a great answer as to what metrics I would suggest, because most of the metrics I've seen in the literature I find to be severely lacking, to be quite honest. And I think that's an area of both future work and also an area where system designers need to think about, what are they actually looking to do with flexibility and adaptability in their system. So, flexibility and adaptability for designing an iPhone is very different than for designing surface combat systems, right? And so there's also the aspect of a lot of these things are specific to each system as well. So might be an unsatisfying answer, but that's what I've got.
I hear his frustration as well with respect to the definition of the different abilities, not just the so flexibility and adaptability. But the thing that I would add there too is that I agree that there's probably not going to be a precise definition and nail down what that actually means. So, but circling back to what the chair alluded to right after my presentation was talking about bringing in those end users early on, and I agree with that. But I also would say too that those end users are critical throughout the whole life cycle of the system to learn from, and so what I would say to that too is that with respect to flexibility and adaptability, I see that more as a scale of what that really means. And again, that kind of circles back to the Likert type scale that I was talking about earlier. And then so what I would like to see with that flexibility and adaptability would be, what is the fleet saying? What are they saying about the flexibility of, and the way that they understand it in their day-to-day jobs? And I would see that probably as like a spectrum of feedback and input. And so I don't know that you would definitely call that specific, in the SMART acronym, but I think that is usable data and usable feedback. Over.
Yeah, I think those are great observations. And I would say at least the three of us on the panel are probably in violent agreement about this. I would like to recommend to everyone a very impressive work done by our chair of acquisition, Admiral Dave Lewis. He recently wrote in the Naval War College Review a paper entitled Innovation Interrupted: The Next Generation Surface Combatant Design. And in that, he takes a look at both the history and the technology associated with warship design with just this topic in mind, the flexibility and modularity. So it is a treatment of various warship designs throughout history, going all the way back into history. He talks about the early British battleships. He continues on with examinations of aircraft carriers, the earlier and right up into the present. He addresses things like how well submarines performed in World War II, and later how we have done well and not so well in our ability to make ships and their combat systems adaptable and flexible. So I don't want to steal too much of his thunder, but I would tell you that a very, very good read is Admiral Lewis's article in the Naval War College Review. The easy way to get that, it's all online. If you go to the Naval War College website, and specifically to Naval War College publications, you can find it in that section. Again, Admiral Lewis on Innovation Interrupted, the Next Generation Surface Combat System Design. So with that, on to another question. This one from Michael Bobulinski, and his question is, he's curious about the choices of aircraft and some of the considerations. He says that F, or fighter designated aircraft, are not typically used as air-to-ground platforms. CONOPS changes and capability changes allow that F and A designated aircraft, so fighter and attack designated aircraft, are multi-role, and A designated aircraft are air-to-ground platforms. I guess the question is probably for Adit. How much weight was given to the fact that some of the platforms were looking to both CONOPS and modularity changes?
Yeah, so we sort of looked at it as a spectrum of how optimized the design was for the mission. And like we said, there is obviously an interaction effect between CONOPS changes in the form of your system as well. So when we look at it, even though I agree that the sort of F designation for aircraft is supposed to be for primarily air-to-air missions, but I think that the DoD has also sort of relaxed that a bit. For example, the F-35 is expected to take over close air support, which is a decidedly air-to-ground mission type. And so how much the designation is sort of following the letter of the law these days, I kind of question that. But we did consider that a lot of the aircraft that we looked at were not really designed to do close air support. So the F-16 certainly in its original design and conception was not supposed to be some stellar air-to-ground platform, as it were. And that's sort of why we liked this as a natural experiment, because you have platforms like the A-10, which was decidedly, this was designed to do close air support. This was designed for interdiction, whereas the F-16 was designed, at least on paper, for air-to-air combat. But we've seen a lot of these F-designated systems take on more air-to-ground roles than previously expected. And one of the reasons is because of logistical constraints. Jonathon alluded to the DoD having, less money to work with. And so if you can reduce your logistical footprint by operating fewer types of aircraft and making those aircraft do more than they were originally intended to do, that can save you a lot of money, right? But then that also leads to the challenge of, okay, well, an F-16 is just not going to be able to do close air support the same way an A-10 or even an AV-8 or an FA-18 is supposed to do. And so we did consider that, but this is all qualitative work, so we didn't necessarily weigh that, but we did, write about it and consider it when we were discussing the types of changes that are required to get some of these more multi-role systems to do specific missions. So it's sort of an answer of you can have a system that's specifically designed to do one thing and will probably be great at that one thing and maybe not so great at everything else. Or you can have a system that's designed to do everything, but perhaps isn't the greatest at anything. So that's, you know, an interesting thing there. Yeah, thank you for that question.
All right, thank you, Aditya. You know, it occurred to me, I want to lead this next question with a little bit of experience in about the 2013, 2014 timeframe. The Naval Sea Systems Command was asked to come up with ideas for the flexible, adaptable, modular warship. And the American engineers, being you know, just the ingenious people that they are, one of the very first questions they asked was, well, how much is this ship going to cost? And the response from OpNav was, well, we're not going to tell you how much it costs. We just want it to be flexible, modular, and adaptable. And then the very next question, as you might expect, was, well, what's the mission for this ship? And the answer was, well, it's going to do all kinds of things, but we're only going to tell you that. Well, you can imagine the frustration on the part of the engineers with that. So with that little recollection, let me pose another question. This one comes from Michael Bobulinski, and he says, I would contend that it's important for the end user to clearly define their requirements, spell out what flexibility means, spell out what adaptability means from the end user's perspective. Absent that clear definition, there's a risk of getting it wrong in development. So I guess for our presenters, I would pose the question, and I'd open this question as well to the people who are participating. Do we have it wrong in the current JCIDS, the Joint Capability Integration Development System, the requirements generation system? Do we have it wrong? And if so, how can we make it better?
You take the lead on that question?
Sure.
Okay. So I'll just speak from my my perspective on this and what I think of you know, requirements so the way I see, I agree that that they, to the extent that you can, clearly define them, right? So there needs to be in my perspective, with respect to the end users, there should be a lot of elicitation, right? The systems engineer, the engineers in general, cannot, in my opinion, cannot expect the end user, sponsor, whoever, to dump the complete set of requirements for them, from which they would take those stakeholder requirements and then, you know, turn them into, you know, system requirements and functional requirements, et cetera, design requirements, right? So from my perspective, there needs to be a lot of elicitation. So as the chair just said, you know, there was a lot of kind of like, we'll tell you later with respect to his example, right? And then from that too, the elicitation shouldn't, in my opinion, also shouldn't just be the end user, even though I'm talking a lot about the user experience system, right? I see requirements gathering kind of like as like a dartboard, right? So in the middle of it, you know, you have you know, the requirements of the end user, and the mission's goals and all those types of things that are important, right? And on the outer edges of it, you have the different mandated requirements. So the chair talked about Mill Standard 901D earlier, right? So that's, or is it E now? The shock and vibe requirements. So to me, that's a requirement, right? But it's on the outer edges of the system design. You have to meet certain, if it's class A, class B, shock, etc. But then I think there's also, there's places in between too that should be considered, like the requirement, and it's kind of weird to think in my perspective to think of it in these terms, but like the bad guy requirements, right? So what are they going to do to hurt the system, right? And those requirements should be considered. So from my perspective, yeah, I agree that that the requirements should be spelled out, like what the different, you're talking about flexibility, adaptability, et cetera. And again, I go back to the spectrum, but I think that a lot of elicitation and thinking in terms of all the different players that are going to be coming into the system, and including the bad guys, the environment, the standards that you're going to have to adhere to, all those need to be integrated into developing the system requirements. And then from that, when there's not a clear delineation of what terms mean, or if there's conflict, right? So if I'm building a system and somebody wants a lot of power, but then the ship needs to have the space cool at a certain level degree, right? That wattage is kicking out high BTUs, and so there's a conflict there. So there's a spectrum, right? And there has to be some kind of middle ground. So that's the kind of way I see it is that a lot of elicitation, considering the broad range of requirements, and then trying to find the spectrum to which you can bound those particular requirements as you can. Over.
Yeah. Thank you, Jonathan. So a couple things occur to me, and that is, again, as the chair of Integrated Air and Missile Defense, one of the things I am privileged to do is to work with the Meyer Scholar program here at NPS. The Meyer Scholar program, named after Rear Admiral Wayne E. Meyer, the father of Aegis, and the source of a great deal of illumination when it comes to combat systems design and development. And Admiral Meyer, sage that he was, understood that, and what he taught us was that when it comes to warships, one of the things that we need to recognize is that generally the warships reflect a capital investment on the part of the Republic. And generally, those capital investments are very, very expensive, and particularly for the ships that are larger, the aircraft carriers, the large deck amphibious ships, even the destroyers, like Arleigh Burke class example. Those ships are going to be around for a long, long time. And then, given the character of war being what it is, that it is ever changing and increasingly more rapidly these days, that it's really very important for us to understand how this modularity, this flexibility, adaptability comes into play. So with that, I'd like to go back to the questions. Lieutenant Josh Hudson, Meyer Scholar extraordinaire, has a question for Aditya. His question is, how much do cultural differences between military branches affect the prospects for or receptivity to post-production changeability? Is there any difference among the branches for the prospects or receptivity of this post-production changeability?
Yeah, that's a good question. Someone else in our lab has sort of taken a stab at that. she's with the Special Operations Forces, and she sort of argues that the services that more prioritize people over machine are better able to have their users initiate change in a lot of these different systems. I don't think I've seen a broad characterization of service X and service Y do a better job than service Z, but I do think there is a culture of, if you trust the end users enough to come up with good ideas and make changes, they can initiate change on their end. And it doesn't always come from the manufacturer that's not in the field with them, right? So I'm not going to say one service over the other, but I do think culturally speaking, when we trust the end users of our systems to know what they're doing, know what they actually need over what our contractors are telling us that we need, I think that type of culture can facilitate better post-production change. Because, you know, a lot of times we do see these ConApp changes being initiated by end users and warfighters rather than, you know, a contractor. So I think I've seen a lot of examples where the warfighter might come up with a good ConOps change that comes up with a new capability rather than waiting on the contractor to roll out a very expensive, maybe long development cycle module instead. So I think if the culture sort of shifts to, you know, let's trust our warfighters in the field to actually create and implement change rather than waiting around for contractors or whomever to get these changes rolling and tell us what we need to do. I think that opens up the door to more post-production change.
Yeah, that's a great question and a great observation on that point. For those who are not necessarily familiar with this, and this goes to Adam Pollock's observation about maybe we have it wrong. Maybe we should be working in capabilities based. And the point that Aditya brings up, I think, is very, very important. Again, for those not familiar, rather than the difference between the various service branches, rather between these cultures. So you have the service culture, but then you have the operator culture. Best example is in special operations, where indeed they do pay a great deal of attention to the operator, the user, and that it's not just that. So if you don't know, Special Operations Command has special authority. So the commander of Special Operations Command is the acquisition executive for special operations. And that is a very, very powerful combination.